Recording.
All right. Okay, hi, my name's John Mandelbaum. I'm the owner of Bauer Research, and I'm going to present a few demonstrations today which are going to demonstrate that conservation of angular momentum is a fallacy. Basically, I've been working on a few projects. I'm not going to discuss what they are. However, the prototypes that I produced didn't work. And this caused me to question what was going on. And eventually I questioned the law of conservation of angular momentum, and how I proved this to myself that it doesn't work is through this little device here. This is basically a marble drop device which takes one path running in a constant radius circle and another in a reducing radius circle. And the basics are that this radius reduces by about a third of the original, and based on the conservation of angular momentum, V2 being R1 over R2 times V1, the second radius being 1/3, this should result in about a threefold increase in the velocity of the marble going through the reducing radius turn. And I'd like to just give you a quick demo of how the operation works, and we're just going to drop these two marbles through here, and you'll see quite clearly that both of them go at exactly the same velocity. You're going to follow the marbles where they go over the table. Can you see them?
Mm-hmm.
Okay, I'm just going to do it again to make sure, and here we go.
Yeah.
Fortunately, I have a third set of marbles. There we go. Oh yeah, all right. In any event, you can clearly see that there is not one marble going 3 times the speed of the other marble. And that is because conservation of angular momentum is a fallacy. However, I'm aware that there are going to be some of you who are questioning whether conservation of momentum will apply to a marble drop, and the more advanced of you are already thinking of reasons why this doesn't demonstrate it and so on. So I've prepared another demonstration. This demonstration is going to be straightforward, pretty simple. An object rotating on a tether. Now, I've marked off 2 radiuses on the string, one at about 5 centimeters and the other one at about 50 centimeters. Okay, and here's the calculations for this demo. Mass is about 20 grams. It's a little more than that, but this will do for the purpose of calculation. Radius 1, half a meter. Radius 2, 5 centimeters. Angular velocity, I'm going to try and swing it about 1 time a second. Obviously it's not perfect, but you know, for purposes of what I'm trying to show here, it's sufficient. So your angular momentum is about 2 pi radians per second. If we want to work out the velocity of that, well, velocity 1 is your radius times your angular momentum, so it's a half times 2 pi, so it's pi meters per second. And your velocity 2 then is clearly 10 times that based on this equation here, because radius 2 is 1/10 of radius 1. Okay, and if we take this a step further and work out the centripetal force, which by the way has an equal and opposite force called centrifugal force, which some fools call imaginary, but that's another story for another day. Centripetal force, the formula for that is F equals mv squared over r, and if we apply the values in there and work it out with a calculator, if you like, comes to 395 newtons. 395 newtons, what's that? Well, that's about the force that gravity exerts on 40 kilograms. So the theory is that when I swing this around at 1 turn a second, and I pull the string through from here, from this point here to this point here, this should be exerting, I should be having to pull about 40 kilograms, the equivalent of lifting 40 kilograms. That's the first thing. Second thing is, if we apply this theory here, then since R2 is 1/10 of R1, V2 is going to equal 10 times V1. All right, that's the first. Second thing that you have to think about is that since your radius is 1/10 of the original radius, your diameter that the object is going to traverse is now going to be 1/10 of its original. And if we look at the angular momentum of that, V equals R times omega, then omega being angular momentum is V over R. If velocity is times 10 and R is divided by 10, then omega is going to be times 10, right? So, sorry, times 100, okay? So in other words, me swinging this at 1 revolution per second, when I pull it in, should produce 100 revolutions per second. Now 100 revolutions per second is 6,000 RPM. I'm sure that that kind of gives you an idea of what speeds that we should be talking about here. So let's do this little presentation here. Okay, as we can see, this is a string going through a small hole in a tube, not a very long tube, but nevertheless. This is a tether, and here's an object. Okay, I'm going to try and do this without knocking my head in. I'm pulling it up to the first mark on the string, and we swing it at about 1 meter per second. And we pull it in. Now, I don't know about you, but I can assure you that's not 40 kilograms that I'm pulling on that string. And that thing was not doing 6,000 RPM. It was doing more like 10 revolutions a second, which is the reality. Why is this the case? Well, the reality is that conservation of angular momentum, and this equation here, is false. The reality is that V1 equals V2, and the reason for that is because linear momentum is conserved, like we saw in the marble experiment. That's